Okay, chapter 7 is atomic and nuclear physics. This is basically divided into three portions. First portion is about the atomic and nuclear structure. Second portion is about radioactivity, and the third portion is about nuclear reactions, fission and fusion. Okay, so the first portion, atomic and nuclear structure. So first in the atomic structure comes the Rutherford model of the atom, where basically they have a dense positive nucleus and electrons around it, and the electrons are orbiting the dense positive nucleus because of electrostatic attraction. So you need to basically go through the notes. The notes are very well explained in this part. The experiment that actually led to the Rutherford model was the alpha particle scattering. Okay, you can go into the details in the notes. The significant features about alpha particle scattering that the students need to remember are the three observations and their respective interpretations. So the observation and its interpretation. So observation 1 was most alpha particles. Okay, as a background, what happened in this experiment was there's a thin gold foil and alpha particles are basically shot across the gold foil, and there's a detector at the other end, and there's a detector all around in fact, and what they do is they see how the alpha particles scattered when they pass through the gold foil. So the first observation is that most of the alpha particles pass straight through the gold foil. Okay? This shows that most of the atom actually consists of empty space. Okay? Second observation is that some of the alpha particles were deflected at small angles less than 90 degrees. Okay? So some were deflected at angles less than 90 degrees. Okay? This shows that within this empty space there is a positively charged nucleus. Okay? So that positively charged nucleus is actually repelling the positively charged alpha particles and deflecting them at angles less than 90 degrees. Okay? So there's a positively charged center. Now the third one, very few of the alpha particles went and hit the gold foil and came straight back through. Now that was very unexpected. It's almost like shooting a bullet and seeing it ricochet straight back at you. So what that shows is that by conservation of momentum, you would realize that not only is that central nucleus positively charged, it is also very massive, and because of its massive size, because it is massive, it could actually reflect the alpha particle backwards. So some of them, few were deflected at angles greater than 90 degrees. Okay, this entire observation interpretation table is made on page 3. So this shows that the center was massive. Now massive does not mean a large size. Massive means that it had a large mass. Okay, so remember, an atom, if you have to scale it up, it's pretty much like the electrons are orbiting in if they're orbiting in the space of a football field, right? The massive nucleus is just the head of a pin in the football field. So that's the correlation between the size of the nucleus and the empty space in the atom. So you must make sure that the students understand that massive does not mean a large size. Okay, so after this, the student should basically interpret the observations in this way, because the exam questions will basically ask questions based on these three observations. Now, the next portion is outlining limitations of this basic model. The student should be able to outline at least one limitation. So limitations would be 1. It's quite clearly mentioned in the notes, but just for reference sake, 1, this model does not tell you the composition. composition of the nucleus. They only mention that the nucleus is positively charged. Okay. Second, it cannot explain why the electrons, when they're moving in an orbit, why don't they eventually lose energy and spiral back down into the nucleus. Okay. So it can't explain why electrons not drawn to nucleus. Okay, because if the nucleus is positively charged and electrons are negatively charged, obviously by electrostatic attraction they should lose energy and fall to the nucleus. And the third point is, if the nucleus is consisting of positively charged particles, why don't these particles fly apart if they are repelling each other? So explain why protons don't fly apart. Okay, so these are the three things that can't be explained. Now the composition of the nucleus is basically explained. It comes in a later model when they actually define. We now know that there are also neutrons that are held together with the protons in a nucleus. Okay, and why don't the protons fly apart? Because of this force that we now know called the strong nuclear force. Okay. Okay. And not only does the strong nuclear force help, also the existence of neutrons. Okay. All these strong nuclear force and the neutrons help to bind the nucleus together. How? We will see in a later part. The strong nuclear force is about 100 times stronger than the electrostatic force of repulsion, but the thing is that it only comes into play at a certain distance. So we will see how this works later, that the strong nuclear force only acts at 1.3 femtometers of distance. So if two protons are at 1.3 femtometers apart, then they will be attracted to each other by the strong nuclear force. If they are even slightly disturbed from that distance, they would be repelled by electrostatic repulsion. Okay. Now, this part, explain why electrons are not drawn to the nucleus. This comes from the fact that electrons don't just exist randomly in any energy zone. They actually exist in discrete energy levels. And the evidence for this is the next part, which is the line spectra and the absorption spectrum. So you have to know about the emission spectrum and the absorption spectrum. So evidence for atomic energy levels. So when we say atomic energy levels, we are talking about the energy levels of electrons. Okay. You have the emission spectra, and the absorption spectra. Okay. Now 7.1.4 basically explains how the emission spectrum and absorption spectrum work. Emission spectrum, what they basically do is they pass a high voltage through a gas, and the gas used is monatomic hydrogen gas. So when they do that, the high voltage actually excites the electrons to a high energy level, and when these electrons, when they are excited from a ground state to another energy level, let's say the electron was originally here, it gets excited and comes here. Now, once it's in an excited state, it will fall back down to its ground state. And when it does that, it will emit a photon. Okay? This photon is actually emitting the energy that is lost by the electron. And this photon must be of a particular wavelength depending on the energy difference between the energy levels. And therefore, if we actually detect a spectrum of the wavelengths of these photons, we will see that the photons have discrete wavelengths, and that is what is observed, as you can see on page 4, that the line spectra has discrete lines in a monatomic gas such as hydrogen or neon. Then in part B, you can see that again you have discrete energy levels in the band spectra of a molecule. So molecules have a complex relation between the atoms, which produce multiple energy levels for the electrons to exist in, and therefore you have a band spectra. But again, the fact remains that they are a discrete spectra. Continuous spectra is obtained from matter like solids or plasma, liquids. Why? Because in that the electrons can exist in multiple energy levels. They are not quantized in solid matter, solid or liquid matter. Okay, absorption spectra is simply the opposite. What happens in absorption spectra is that you have a filament lamp at a high temperature, and this filament lamp is going to it basically passes light through a sodium discharge tube, and which has a gas at a low pressure and temperature. So what happens is that this filament lamp is giving away photons of various wavelengths. Okay, so when it reaches the sodium discharge tube, the sodium discharge tube has atoms which have electrons existing again at discrete energy levels. Okay, so now when the particular photon appears here, which is going to excite this electron to the next energy level, this photon will be absorbed and the electron will be moved up to a higher energy state, whereas the rest of the photons will pass through. Okay, and when this electron falls back down, the photon that is emitted in various directions. Therefore, when you see a spectrum here, all the wavelengths will be bright except for the wavelength which corresponds to this energy level. That energy level will have a dark line, as the photons absorbed were emitted in various directions. So, so this is basically the converse of what we saw in the emission spectra. And when you compare the absorption spectra and emission spectra of the same gas, you will actually see that the dark lines in the absorption spectra will correspond to the bright lines in the emission spectra. So basically two different methodology of showing the evidence for existence of atomic energy levels.